So good evening all of you, welcome you all back onto this series on engineering mathematics. So we have started differential equations in some lectures back actually. So in today's class we'll be again looking at differential equations, but of course with the exact equations. Okay, yeah, good evening Ram. So let's see, this is lecture number 4 of differential equations, ordinary differential equations. Of course, good evening all of you. Yeah, so before I start, I would like to give you a quick update on the Telegram channel, on which all the updates on this English channel are posted actually. So this is the Telegram channel link for the Wallah English Telegram channel, so that any content that's coming up on this channel will be posted here, so that you'll be in sync with the content that's flowing out and you won't miss anything. Okay, similarly this is my personal Telegram channel, of course maintained by me and my students at PW. So if you wish to get in touch with me for anything or any help or any guidance from us, you can just post the questions or whatever the points you need in this group. Definitely me or one of our students will definitely answer it. Okay, and you also have this PW Unity. I also strongly recommend you to basically download this Unity and register yourself, so that you can have a track of all your questions at a particular location. Okay, so when you are typing a doubt, if you type exclamation doubt and if you type exclamation note, then these points get stored in your Unity login, so that whenever you have a doubt at the second time when you are revising the topics, you can again go back there. Okay, so these are the quick updates of the platforms. And in the last lecture, of course the last lecture was very short because of certain issue with the devices, but till now what we have covered is review of the last lectures. We have started with the differential equations. Of course we have broadly divided them into ordinary differential equations and partial differential equations. Okay, so we have also talked about order and degree of the differential equations actually. So ODEs is what we started looking at, and once we have started looking at ODEs, we have solved, first of all we have looked at forming of ODEs, and we were doing solving of first order equations. Okay, solving of first order equations. So when we were solving this first order ODEs, we got some interesting things like the variable separable form, where the function, so the first order ODS is generally of the form dy by dx is equal to some function of x comma y actually here. Okay, or else this can also be written as some function of x comma y dx plus some function of x comma y dy is equal to 0. I have shown you that how this can be replicated like this. You can basically solve this in any one of the forms. Okay, so we have talked about variable separable form actually. Then we started looking at homogeneous equations. All these are the solving techniques of first order. In the last lectures we have seen. So homogeneous equations actually. Okay, so in the homogeneous equations, this m comma n are of same degree, are homogeneous functions, of same degree actually here. Okay, so these are homogeneous functions of same degree. And then we started looking at non-homogeneous equations, actually. So when we looked at these non-homogeneous equations, we were looking at two cases where the equations are of the form dy by dx is equal to ratio of two linear functions, in which one case both these linear functions have same slope, in the other case they don't have same slope. Of course they have different slopes actually. Okay, so we have seen two cases and we have seen the techniques to solve all these equations. In today's class we'll be focusing on exact differential equations, then integrating factors. Okay, so we'll see what is an integrating factor and what's an exact differential equation, and also linear differential equations actually. Okay, so in today's class these are the things which we are going to focus in today's class. So till last class, means basically till this particular point, is this clear to all of you, everyone? So please confirm in the chat box. Till the last lecture these were the topics which were taught. So is it clear to all of you? Homogeneous means all term degrees are same. Yes, of course. Okay, then only when you substitute kx in place of x and ky in place of y, you can pull out k power n as common. Okay, otherwise if some term is of say third degree and if some term is of second degree, you cannot take k cube common. Okay, that's the reason. Fine, then let's solve this exact equations. So in the last class we were talking about the exact equations. An ODE m of x comma y dx plus n of x comma y dy equal to 0 is said to be an exact ODE an exact ODE if there exists a function, say f of x comma y, such that this value m of x comma y dx plus n of x comma y dy is equal to 0 is, basically this value is equal to derivative of the function f of x comma y actually here. Okay, so that's the derivative of the function. So I have told you the name exact comes out this left hand side of this equation being the exact derivative of the function f of x comma y actually here. Okay, and when this happens, then there is some mathematical condition which should definitely happen. Look, I've told you, since f is a function of x comma y, in chain rule, basically whatever I have taught you in in multi-variable calculus, I've told you one thing. So chain rule of differentiation, I've taught this actually here. Okay, so we have done chain rule of differentiation. So when we are talking about chain rule of differentiation, I have given you, if there is some function which is depending on n variables, let's say x1, x2 and so on till xn, then any change in this function is calculated as summation I equal to 1 to n dou f by dou xi times dxi actually. Okay, do you remember this? Yes or no? Please confirm it in the chat box. If a function is depending on n variables, then if you want to calculate the change in f because of the changes in all these n variables, we take the changes in the function due to each variable separately and then we sum up all the things. We have seen this in the multivariable calculus. Can you recollect it? Yes or no? Come on, quickly type it in the chat box. 2. Did we discuss this? Yes or no? It's a chain rule of differentiation basically. Yeah? Forgot. Last week hardly we were discussing it, right? Can you all recollect this? We have taught this in the multivariable calculus, of course. Okay, when we are talking about the partial derivatives, then we have looked at something called chain rule of differentiation, and this is what I have taught. So clearly, if f is function of x comma y, this tells you df is equal to dou f by dou x, treating y as constant into dx plus dou f by dou y treating x as constant times dy actually here. Okay, now if this is what it happens, and it's an exact derivative obviously, so this is an exact derivative, d of f, small change in f is the exact differentiation. So you can observe, if you compare these two, okay, if you compare this first, basically if you call this equation 1 and you call this to be equation 2, so from 1 and 2 you can observe something. From 1 and 2 you have this function which is the product of dx is basically this function, correct? So m of x comma y is equal to dou f by dou x, n of x comma y is equal to dou f by dou y actually here. Okay, so this is dou f by dou y. Now try to understand, if this is a function f which is a function of both x comma y, it's also differentiable, we are differentiating it, then ultimately we can have dou square f by dou x dou y should be same as dou square f by dou y dou x, correct? This order of differentiation should not matter for us. If this order of differentiation should not matter, then this can be written as dou by dou x of dou f by dou y, treating x as constant of course, and this can be written as dou by dou y of dou f by dou x, of course treating y as constant here. Now clearly it tells you this quantity is nothing but dou f by dou x is nothing but this function m. So this function is m actually, and this function is n actually. So this tells you, it gives up a condition dou m by dou y should be equal to dou n by dou x actually here. Got it? So this is a mathematical condition which is necessary and sufficient to check the exactness of the differential equation. Okay, but the definition of exactness is not defined by this mathematical condition. Clear? This is just a mathematical check to check whether a given differential equation is exact or not. Clear? The actual meaning of exactness is basically this function should exist, f of x comma y, such that this differentiation is actually exact derivative of that function. Clear to all of you? Okay, so can you all get this? Dou m by dou y is equal to dou n by dou x. Fine, many of you might have seen this. Okay, And normally there is many issues for people in remembering this equation. Okay, sometimes they mess up, they write dou m by dou x equal to dou n by dou y, all these things. So to avoid this, I just give you one useful tip. You can remember this word Netflix. Okay, so you can remember this word Netflix, so that this n and x combination is always there. Okay, so n always comes with x. So if you know n always comes with x, then m always comes with y, obviously. Okay, that's how this formula can be remembered. And when you are writing m dx plus n dy, so out of x and y, x comes first. Out of m and n, m comes first. Okay, so m dx plus n dy equal to 0 is the equation. Got it? Fine. Okay, everyone, Piyush, Shravan, Manohan, Rambabu, Prakash, Ram, I could read only these names, of course. So please type it in the chat box. Is this clear to each and everyone till this point? Because many times people used for thermodynamic relations also. Yeah, maybe I might have used same thing, because we'll see lot of applications of differentiation, integrations, all these things in the thermodynamics as well. Fine. So let's see, and this is the chain rule of differentiation, which is a bit important stuff. Again, we had enough discussion on this. Now, what is the advantage if a equation is exact? Okay, so that's a test for exactness, of course. Okay, but why we are interested very much in calculating exact equation? Okay, so for that, let us see why we are very much interested. We have solved few questions in the last lectures to have some nice idea. So let's see. We had differential equations 3. Yeah, no, last lecture is 3. So in 2 we had some nice discussion. Okay, so this is one of the class notes which we have solved in couple of lectures back. Okay, lecture number 2. So here in this case, after solving this first order variable separable equations, we have solved homogeneous equations. You take this equation for example. Okay, so let's see. Before considering that equation, I'll tell you one thing. If m dx, this is a function of x comma y, dx plus n of x comma y dy is equal to 0 is an exact dE, then the solution of the dE, is integral m of x comma y dx treating y as constant. In this integration, when you are performing this integration, we'll treat y as constant, of course. Okay, plus, good evening Vijay, plus integral terms not containing x, in n of x comma y times dy is equal to constant. Okay, so that is equal to some arbitrary constant. So once you know that the differential equation is exact, you can write the solution in a single line like this. Okay, so let's see. Example, solve. Let us take the same equation. Okay, 2x plus y dx plus, this is x plus 2y dy is equal to 0. X plus 2y dy is equal to 0 actually. Okay, so this is one differential equation. In order to solve this equation, we figured out that it's a homogeneous equation. Then once you know it's homogeneous, you have substituted y equal to vx, then you have substituted and simplified a bit. So after doing a bit of integration, substituting back, after a lengthy process, you figured out x square plus xy plus y square is equal to constant is the solution. Okay, so let's see here. First of all, let us check this is exact equation or not. So clearly this is the function m of x comma y, and this is the function n of x comma y actually here. Okay, so let's say m of x comma y is equal to 2x plus y, n of x comma y is equal to x plus 2y. So this tells you dou m by dou y is equal to how much? If you differentiate this term partially with respect to y, you will get 1, correct? Because 2 is a constant. When you are differentiating with respect to y, x is a constant, so the derivative of the first term is 0, plus the derivative of y with respect to y partially is 1, so this guy is 1. And what about dou n by dou x? Dou n by dou x, clearly again if you differentiate this with respect to x partially, it is 1. So clearly these two are equal, so it tells you that it's a exact ODE. Okay, so this is a exact ODE. If that's exact, then let us follow this procedure. integral, therefore solution is integral treating y as constant, m 2x plus y dx plus integral terms not containing x in n. So clearly this n has two terms, one is x and one is 2y. Okay, so out of these two terms, this is the term which do not contain this is the term which do not contain x, and this term contains x. So out of these two terms, we'll consider only this particular term because that's the only term which do not have any involvement of x actually. So plus 2y dy is equal to constant. So if you integrate this, let's see, if you treat y as constant and if you integrate this with respect to x, integration of 2x is x 2 into x square by 2, 2 gets cancelled, you have x square, plus if y is a constant, integration of y with respect to x is y times integration of 1 is x, plus integration of 2y dy is y square is equal to constant. That's it. Okay, so this is the differential equation which you have solved in one line, but the same solution here we have obtained using a bit of very lengthy calculations actually here. Got it? Did you all understand this? Yes or no? Please type it in the chat box. Vijay, Piyush, Rambabu, everyone, of course. Did you all observe what happened here? Within a single step, we were able to write the solution of the same differential equation which we have solved using many steps in the previous lecture. Got it? That's the power of exactness equation, of the equations ODEs being exact. If the equations are exact, you can write the solution in a single go, of course. Okay. Fine. Okay, so that's the solution. So 2x may be x contain y I choose because this is m. Okay, this is m. I'm telling you, you will keep m as it is and you will integrate with respect to x. But when in the second integral in n of x comma y, you will treat terms which do not contain x. Okay, so you should choose terms not containing x only from n. Okay, in the second integral. First integral is as it is. You will just dump the function m and you will calculate. Got it? Means one question can be solved one or more method. There are many methods of course solve anything. Okay, so let's see. Let's take an example of one more problem which we have suffered a lot in the last lectures. So let's look at it. Maybe one question which we solved. Yeah, I think this question anyhow is simple question which I have said that day to show you homogeneous. Yeah, coming to these questions. So let's see this differential equation. Okay, so solve. What is the equation I have given you? X plus 2y plus 1 dx m dx plus n dy, 2x plus 4y plus 3 dy is equal to 0. Okay, so this is what we get. Clear? This is the equation what we got. In exam we must remember this because first the marks, if I have maximum 2 marks, so time also limited. First of all, in GATE examination, what are the questions that comes from differential equations are very simple. Okay, yeah. So let's see if this is the equation which we have solved. Okay, so here you can see we have started this example here. We figured out something and then we made some substitutions. Then we have done splitting, integrations and all. Finally, we got the answer. Okay, so let us check here whether the same thing will obey or not. If this function is m of x comma y and if this function is n of x comma y, okay, because this is coefficient of dx and this is coefficient of dy. Be careful, sometimes in exam to basically w, they'll give dy here and they'll give dx here, then this is not m, okay, this is n, because m is always that function which is in multiplication with dx actually, okay, and n is that function which is in multiplication with dy. So please check carefully, make sure this coefficient, this function which is coefficient of this dx is always m. Okay, sometimes if they switch this x and y here, you should not get confused. Okay, then let's see. This implies m of x comma y is equal to x plus 2y plus 1, n of x comma y is equal to 2x plus 4y plus 3 actually here. So this tells you dou m by dou y is equal to 2 and dou n by dou x is equal to 2 actually here. Okay, so this is dou n by dou x is equal to 2 actually. So these are 2, of course they are equal at any given point. So let's write the solution. Therefore given equation is exact. given equation is exact. So what is the solution? Therefore solution is integral m of x comma y dx by treating y is equal to constant plus integral terms not containing x in n of x comma y dy is equal to constant actually. Okay, so this is constant. So let's solve this. First, integral treating y equal to constant m of x comma y. So this is m, of course, x plus 2y plus 1 dx plus integral terms not containing x. So here you can see there are three terms, 2x, 4y and 3. This is the term which is containing x, and these two terms do not contain x actually. So 4y plus 3 dy is equal to constant. Okay, so let's integrate this. Integration of x with respect to x square by 2 plus, when you treat y as constant, this 2y itself is a constant, so integration of 2y with respect to x is 2y into x, or which is 2xy if you write, plus integration of 1 with respect to x is x, plus integration of 4y with respect to y is 2y square, because 4 into y square by 2, so it becomes 2y square, plus 3y is equal to constant. So if you take this LCM 2, we have x square plus 4xy plus 4y square plus 2x plus 6y is equal to 2 times of constant is again one more constant. That's it. Okay, so this would have been the solution there. So let's check whether this is the solution we got at that function. X square plus 4xy plus 4y square plus 2x plus 6y. X square plus 4xy plus 4y square plus 2x plus 6y is equal to constant. Got it? So that's why this exactness is very important. Like you see the same question we have solved using so much substitutions, all these things. Okay, but in general that did not happen. Okay, so is this clear to each and everyone? Please type it in the chat box. Got it? Did you all understand the advantage of a differential equation being exact differential equation? The solution can be written in a single go actually. Okay, fine. So meanwhile, I've given you one question actually as a homework question which could be helpful. So did you all solve this question? If you have solved, enter the answer, single choice, 30 seconds. If you have solved, then you can enter the answer directly. Come on, do this. Okay, done. So let's solve this question. It's a nice question basically. Given it looks like it's higher order, but you can actually solve this very easily. Is equal to 3x minus 2. That's the question. Okay, so this is equal to 3x minus 2 of course. Then can we write option A maybe? Okay, let's see. So this is equal to d by dx of dy by dx is equal to 3x minus 2. Can I write it like this? It's a just simple manipulation. So d by dx of this dy by dx is actually d square by dx square is equal to 3x minus 2. So what we can do is we can multiply this dx here. Okay, and if you integrate on both sides, so this tells you integral of derivative gets cancelled and you have dy by dx is equal to integration of 3x minus 2, 3x square by 2 minus 2x plus some constant actually. Okay, so this is the thing. Basically I have just integrated once on both sides, then this is just a differential coefficient and this is 3x minus 2. So if you integrate this, First of all, what I have done, I have written this d square by dx square like this, and I have multiplied dx on the other side, and I have integrated. Okay, so when you integrate, you got dy by dx is equal to 3x square by 2 minus 2x plus constant. Now let's see, they have given you one condition. Y dash of 1 is equal to minus 3. So what does it tell you? Look, given y dash of 1 is equal to minus 3. You know the syntax when I'm talking about ordinary differential equations, I have told it can be denoted with y dash or dy by dx, whatever. So this tells you at x is equal to 1, dy by dx is equal to minus 3. Okay, so if you substitute x equal to 1 and dy by dx equal to minus 3 simultaneously in this equation, it tells you minus 3 is equal to 3 by 2 minus 2 plus constant. Okay, so this tells you minus 3 plus 2 minus 1 minus 3 by 2, so which is minus 5 by 2, of course. Okay, so c value is minus 5 by 2 actually. So this constant is given for calculating the boundary condition. Okay, then if you replace this c is equal to minus 5 by 2, let us replace it back. Therefore dy by dx is equal to 3x square by 2 minus 2x plus minus 2x plus constant is minus 5 by 2. Okay, so maybe you can write it minus 5 by 2. So what we can do, again, you know, dy is equal to, you can multiply that dx to the other side, 3x square by 2 minus 2x minus 5 by 2, this whole multiplied with dx. So if you integrate on both sides again, so if you integrate on both sides, it's like integral of derivative of y, so which gives you just y is equal to integration of this x cube by 2, because 3 by 2 into integration of x square is x cube by 3, 3 gets cancelled, you have x cube by 2, minus integration of 2x is just x square. Okay, because 2 into x square by 2, 2 gets cancelled, minus 5x by 2 plus some other constant. Okay, so let's call it c1 for example. Okay, so how to get the value of c1? They have given one again boundary condition, y of 0 is equal to 2 actually here. Okay, so given y of 0 is equal to 2, this implies at x is equal to 0, y is equal to 2 actually here. So 2 is equal to, when you put x is equal to 0, these first three terms will go to 0 straight away. Okay, so only c1 is left here. So therefore the function y of x, the solution is x cube by 2 minus x square minus 5x by 2 plus 2, of course. Okay, so this is what you get actually. Clear? So x cube by 2 minus x square minus 5x by 2 plus 2. So you can check x cube by 2 minus x square minus 5x by 2 plus 2, so which is in option C actually here. Okay, so C is the actual answer in this case. It's an easy question. Basically it's like only the differential coefficient is equal to some function, then you can solve it by direct integration actually. Okay, so this method of solving is called solving by direct integration, because if you just directly integrate, you will keep getting the solution. Okay, so C is the correct answer. Let's check if some of you have answered it. Okay, so poll is not working, it's not taking the options, or you did not attempt, or it is enjoying without writing, without solving. Fine. Okay, so let's solve one more question actually, if you can solve. Okay, fine, it's okay, we can solve that later. So let us discuss a bit on integrating factors. Okay, so what are integrating factors? So ultimately you figured out one thing: if a differential equation is an exact differential equation, okay, then writing the solution of that equation become very easy. Okay, but sometimes the equations are not exact, not sometimes, many times, 99% of the times they are not exact. Okay, when equations are not exact, but by using some technique, some manipulation or some simplifications, whatever, if you can convert a non-exact differential equation to an exact differential equation, then writing the solution could be very easy, right? Yes or no? Correct? Can you all recognize this? That let's say if there is a non-exact differential equation for which the calculation procedure is, or the solution procedure is slightly lengthy, but by making some manipulation like multiplying something or dividing something, whatever, if you can convert that equation into exact differential equation, then writing the solution of such equation becomes very easy, right? So we will see what is this integrating factor, of course. Okay, so let's see here. The factor, in bracket it is function which when multiplied to a non-exact dE to a non-exact differential equation, non-exact dE, converts it to exact. Okay, so basically when you take a non-exact differential equation, if you multiply this function on both sides of the equation, of course anyhow one side is 0, m dx plus n dy is equal to 0. So if you multiply with f of x, some function, say let's say alpha of x comma y is the function, when you multiply this alpha of x comma y to m and n, then the new functions which is like m dash of x comma y and n dash of x comma y, they satisfy the condition. Okay, so in such case we can, is this important for gate of any branch or all branches of, okay, like except computer science, this is there in each and every branch. Okay, so let's see non-exact, of course if you talk with the classical branches like mechanical, civil, EC, TEE. Okay, so let's see the factor or the function which when multiplied to a non-exact differential equation converts it to exact. Okay, so let's see example. If you take this function, okay, so say y dx minus x dy is equal to 0. Okay, so let's see what happens here. If you compare this equation, normally y times dx plus minus x times dy is equal to 0. So as per the standard notations, we call this m of x comma y is equal to y, n of x comma y is equal to minus x. So this tells you dou m by dou y is equal to 1, dou n by dou x is equal to minus 1 actually here. Okay, so this is 1 and this is minus 1, and obviously these two are not equal. Clear? So this tells you dou m by dou y is not equal to dou n by dou x. Then if this is not equal, okay, then how do we solve this equation? We multiply this function with some we multiply this equation with some function so that the equation actually becomes exact. Okay, so look what we'll be looking. So this is one step, it is non-exact. Okay, so let's write therefore given dE is non-exact. Okay, and for the time being you call this equation to be 1. Maybe this equation or this equation both are same. So it is non-exact differential equation. Okay, when this is, of course here it's, you can easily solve this question using variables, separables and all, but this procedure what I am solving will hold good for any general questions actually. Okay, so let's see y dx minus x dy is equal to 0, and this is non-exact differential equation. If this is non-exact, let's say multiplying 1 both sides, 1 on both sides by 1 by y square. Okay, so if you do this multiplication with 1 by y square actually here, when you multiply this with 1 by y square, let's check what happens. 1 by y square times of y dx minus x dy is equal to 1 by y square times 0 actually here. Okay, so anyway this term also becomes 0 because 0 into something it is 0. Then this value gives you y divided by y square, 1 by y dx, then plus minus x by y square dy is equal to 0. This is the new differential equation, but in fact this equation and this equation both are same. The only thing you have done is you have multiplied both sides with 1 by y square. So slight manipulation is what you are doing. Okay, now when you get this new equation, so let's call this to be say m dash of x comma y, and this is n dash of x comma y actually here. Okay, then if you check dou m dash by dou y, so when you differentiate 1 by y with respect to y, you will get minus 1 by y square. Okay, similarly when you write dou n dash by dou x, when you differentiate this complete function with respect to x partially, this minus 1 by y square can be taken as constant. Okay, minus 1 by y square can be taken as constant, then you have only x which is left. Dou x by dou x is 1. Okay, and clearly in this case this dou, of course if you take the new functions to be m dash and n dash, dou m dash by dou y is same as dou n dash by dou x actually here. Okay, so this tells you dou m dash by dou y is equal to dou n dash by dou x, of course, and this equation is exact. Okay, so which tells you that this equation is exact actually here. Okay, so that equation is exact. So that's how by multiplying this function 1 by y square we turned out the equation from non-exact form to exact form actually. Okay, so once the equation is in exact form, I think the solution is very much easy. Of course, clear to all of you? Yes or no? Please type it in the chat box. Everyone, did you all get this? Basically this integrating factor, it is called integrating factor. Integrating factor is generally denoted by if, is generally denoted by if. Okay, that's what. Clear to all of you? Yes. Now once this happens, the main question is, now who told me that the factor which I have to multiply is 1 by y square? Okay, this, how do I know? X कहाँ गया? Differentiate किया ना आपने? So when you differentiate with respect to x, then the differentiation of this x with respect to x is this 1. Okay, got it? When you differentiate minus x by y square with respect to x, treating y as constant, minus 1 by y square can be taken out, then you have only x. So dou x by dou x is 1. Okay, bouncing. So how will the question show up again? I mean to say, what is the most important concept in this? All are important, okay? Because if you open PYQ book, you'll have questions from all. Got it? Okay, I want to know one thing. What happens if the questions don't come from the topics you study? Let's suppose you have spotted all the important questions, then learned some astrology, predicted that question will come from here, 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 and you have studied. But let's say if questions did not come from that topic, then what you will do? You will have any alternative in the examination hall then itself, right? So when you are learning it, learn 100%. Got it? The first step cracking up any exam is covering 100% of the syllabus. Okay. Hello. Now the main question here is, this is the point of interest. Okay, how do I know that this is 1 by y square? That's the question. So how to know which I have multiply? Exactly, that's what I'm telling. Okay, so how do I know that 1 by y square is the integrating factor in this? Okay, so let's set up some standard rules to identify integrating factors actually. Okay, so let's see how do we do them. Rules for finding integrating factor. Rules for finding integrating factor actually. Okay, so let's see. First, by visualization. It is something like stunts performed by professionals. Okay, so by visualization. So let's see how do we visualize. Look, if you somewhere see that if you have something like x dy plus y dx, this can be exactly written as derivative of xy, correct? Similarly, if you write y dx minus x dy by y square, this can be written as derivative of y by x. If you see something like x dy plus y dx by xy, this is nothing but derivative of ln xy. Clear? So this is what you have. This is differentiation of ln xy. Similarly, d, if you write this as y dx minus x dy, okay, so y dx plus x dy divided by, so this term divided by, so what I can write is x square plus y square. Okay, so let's say if I write x square plus y square actually here. Okay, so yeah, okay, so let's say if I have written this, So can someone tell me what does this function give you? It's a derivative of some function. What is that? This is actually a derivative of some function. So if you write this x square plus y square little carefully, then this is derivative of some function. What is that? Can someone think and tell me? This left hand side is an exact derivative of some function. What is that? No idea? Then still it takes some time for you to become professional expert. So tan inverse x by y. This is what. Okay. So tan inverse of x by y. Because if you differentiate this, 1 by 1 plus x by y whole square into derivative of x by y dx minus x dy by y square. Okay. So this is what you get. So if you take LCM, y square by x square plus y square multiplied with y dx minus x dy divided by y square. So these two terms cancel up each other. So you have y dx minus x dy divided by x square plus y square. Okay. So this the same thing what I have written. So how these are helpful is, look, I'll tell you. Just this is anyway just for way to show you I have shown. Now let's see. If you have some equation, example, okay, so example, so let's say if I have given you something like solve y dx minus x dy is equal to x square y plus y cube dy. Okay, so let's say I have given some equation like this. Okay, so that's a differential equation, of course. Now once you see that differential equation, okay, practically if you want to solve that equation, you know there are plenty of techniques which we'll see maybe in today towards the end of the class and in the next class as well, in the linear equations case and all. Now let's see, of course this is non-linear but we can convert that. Okay, so let's see in this case how I can solve this. Look, given y dx minus x dy is equal to x square y plus y cube times dy actually here. Okay, you have this. Then I can write this as y dx minus x dy is equal to, from these two terms if I take y common, I have x square plus y square times y dy. Correct? Can I have this? Yes or no? And if you bring this x square plus y square to the denominator, it turns out to be y dx minus x dy by x square plus y square is equal to y times dy, of course. Okay, now if you want to integrate this, now by visualization, if you know that this is exactly the derivative of tan inverse of x by y, for example, then this can be written as, this implies derivative of tan inverse of y by x, sorry, x by y. Okay, so tan inverse of x by y actually here is equal to y dy. So now if you integrate this, okay, so once you integrate this, we get integral of derivative. So integration of derivation gets cancelled and we have tan inverse of x by y on this side is equal to integration of y dy is y square by 2 plus constant. That's it. Okay, so this is the solution, or you can also write it as x by y is equal to tan y square by 2 plus any arbitrary constant would give the answer. Okay, so that's how we can actually solve the equations, when you can spot out the integrating factors just by, or basically this manipulators just by looking at the function. Okay, so once you see this, like you can see, it appears to be a very tough question. Okay, but once you know these things like this manipulations and all using these functions, then you can solve this kind of questions very easily. Okay, but it's not possible always to just spot the convenience of integrals and all just by looking. Okay, it's not always possible. So when you cannot have that, we have the further methods. Like this is only the first method by visualization, which happens like this. But in general, if you cannot visualize, there are further techniques actually. But is this first method, observing integrating factors by visualization, is this clear to all of you? Yes or no? Okay, some of you may feel, how do you know, first of all, where did we multiply the equation? Okay, so there is no integrating factor. When you have this x square plus y square here, if I multiply both sides with 1 by x square plus y square, that's what you have. Okay, 1 by x square plus y square, 1 by x square plus y square cancelled this, so that's the integrating factor. But of course, directly we can manipulate like this. Yeah, is this clear to all of you? Please type it in the chat box. 7 stars. Kuleshwar Singh, Jay, what's the name? Sorry, Tanam Sheikh, Rambabu, Piyush, Chandan. Of course, I think many are there still, but so all of you please confirm in the chat box. Is this clear to all of you? You may feel that I did not use integrating factor, but the actual integrating factor I have used is 1 by x square plus y square. I have used at this step. Okay, I've used this 1 by x square plus y square as the integrating factor at this step. Okay, so let's see. Second thing which you can observe is actually, if m of x comma y dx plus n of x comma y dy is equal to 0, it's a first order differential equation, is a homogeneous ODE, then IF is equal to 1 by m times x plus n times y is what you have. Okay, and in bracket mx plus ny is not equal to 0. Okay, so mx plus ny is not equal to 0. If it's 0, it happens many times that it can be separated to variable separables directly, but in general, if this is not 0, then this is the expression for the integrating factor. Again, I'm not giving the proofs of this integrating factors because they're out of the scope of UG and GATE syllabus, to be frank. Okay, but if you want some nice insights of these differential equations, of this integrating factors exclusively, you can look at advanced engineering maths. Advanced engineering mathematics, first advanced engineering mathematics by 𝐂𝐨𝐻𝐿. So this is the guy who has written a fantastic book on advanced engineering maths, of course, so you can refer that. Okay, or else you can refer any differential books like by Picard or whatever the famous books you have, you can just pick up. Even we have seen in many dedicated books for differential equations, these proofs of integrating factors are not given. Okay, but normally they give the validation in almost each and every book. Like for example, if I multiply 1 by mx plus ny on both sides of the equation, and if I write m by mx plus ny, all these things, then you know, basically we can show that this is an integrating factor. Okay, in general we see that this is not derived. Okay, but its validation is shown. Like if you want to show validation, I can show you. It's very simple. See, this is, let's say, non-exact equation. Okay, and if this is integrating factor, let's see, if you multiply this 1 by mx plus ny here, the equation becomes, I'll just show you roughly, for m dx plus n dy is equal to 0. Of course, m into dx plus n into dy is, m and n are functions of x comma y. If you multiply this equation with this integrating factor, m by mx plus ny dx plus n by nx, sorry, mx plus ny dy is equal to 0 actually here. Okay, so this is the function. Now observe carefully, in this case this whole thing is actually your m dash of x comma y. Okay, and this complete guy is n dash of x comma y. Then if you calculate dou m dash by dou y, you will end up with, so if you differentiate this with respect to y partially, so let's see what you get, mx plus ny into differentiation of m with respect to y actually. Okay, because we are differentiating with respect to y, you have dou m by dou y minus first function into differentiation of second function with respect to y. So differentiation of this function with respect to y is x into dou m by dou y plus n into 1, so n plus y into dou n by dou y. This is what you get, divided by mx plus ny whole square. Okay, so this is mx plus ny whole square. Then you can figure out some cancellations, like you can check mx dou m by dou y, or you can say m into x into dou m by dou y, m into x into dou m by dou y. This term gets cancelled. N into y into dou m by dou y, n into okay, you have only this term. Okay, so n y dou m by dou y, and you have m y dou n by dou y actually. Okay, fine, let's leave it like this. So you have n into y into dou m by dou y minus m into n, so there is minus mn minus m into y into dou n by dou y. This is what you get actually. Okay, so this is the numerator by mx plus ny whole square. Similarly, if you calculate dou n dash by dou x, you will end up with the same thing. Okay, you can check, you will have the same function, just you can do the differentiation of this function with respect to x partially, like how I have done for y. If you do, you will see both are equal. Okay, so that's validation, but the the derivation of this 1 by mx plus ny is not generally given. Okay, but this validation is shown in few books, some advanced books of differential equations, which anyone can do, of course. Okay, so anyway, this point is just to show that it actually forms an exact equation. Okay, so I'm just erasing this because anyway it's just to show some mathematical understanding. Okay, then let's see, this is the case third. Well, the dE of the form, y into some function involving product of xy dx plus x into some other function, say g of xy dy is equal to 0, which tells you that this is some function which is containing product of xy. Okay, like you can see, like for example f of xy is equal to, say, x square y square plus 2 times xy plus 1. Let's say you have the term like this. Okay, so when you have the term like this, this is something like xy whole square plus 2 times of xy plus xy whole power 0 actually. Okay, so this is a function which consists of, normally you will see functions of x, functions of y, but this is the function which contains terms involving product of both x and y actually here. Okay, so such function. Similarly, g can be some other function, say for example e power xy plus x square y square by 2, something like this. Okay, so this is also a function which involves only the terms containing product of x and y. Okay, so in such cases, if this is the case, then integrating factor 1 by mx minus ny mx minus ny is not equal to 0 again. Okay, because again in these cases, if it's equal to 0, majority of the times it can be solved using homogeneity or variable separable forms. Okay, but in general, if this is not equal to 0, 1 by mx minus ny, so this is plus and this is minus. Please keep a note of this. Okay, then fourth, for m dx plus n dy is equal to 0 if 1 by n times of dou m by dou y minus dou n by dou x, this value, if it's coming out to be some function, say only a function of x. Okay, so this calculation for this function is coming out to be only a function of x, then your integrating factor if, then if is equal to e power integral, so let me write little bottom so that get merged. So then integrating factor is equal to e power integral f of x dx actually here. Okay, so that's the integrating factor. Of course, I'll pick up an example for this and show you what happens. Then the fifth one is the last one, hopefully, at least within the GATE syllabus limits. Well, m dx plus n dy is equal to 0 if 1 by m times dou n by dou x minus dou m by dou y is only a function of y purely. Okay, then integrating factor if is equal to e power integral g of y dy actually. Okay, so these are the standard procedures in working out the calculations of integrating factors. Okay, so that's what you have. Clear to all of you? Yeah, yes or no? Please type it in the chat box. Yeah, is this fine to all of you? Can you all understand this? Because I've just given you the expression so that you can easily put the values of m and n depending on the question what they give you, and you can figure it out. Okay, so this is the way how we calculate the integrating factors actually, but anyway, this is just for the idea I have given you, some idea. Okay, and this is a good maths book, follow. So now if these are the integrating factors, then ultimately you can multiply the given differential equations which fall in one of these categories with the corresponding integrating factors, and you can get the answer actually. Okay, so let's see linear equations. So what are these linear differential equations? Okay, so we will figure out one equation and then we'll also solve the general form of the linear equation actually. Okay, so let's see. Linear differential equations tells you an ODE is said to be linear if the differential equation doesn't involve terms containing one higher powers of dependent variable. Okay, so it should not involve the terms containing higher powers of the dependent variable. Like example, okay, please mark this doesn't. Okay, otherwise people feel that they should be there. So if the DE does not, okay, so it does not involve terms containing first higher powers of the dependent variable like y square, y cube, y power 4 and so on, etc. Okay, so these things should not be there. Second, higher degree differential coefficients, So any differential coefficient should be only of first linear, so first degree. Okay, means basically you can have dy by dx, you can have d square y by dx square, because that is second derivative, not dy by dx whole square. Okay, dy by dx whole square is the second degree term of a differential coefficient, but d square y by dx square whole power 1 is a first degree term of the second derivative. Clear? So that's why you should have differential coefficients only of linear powers. Clear? So linear higher degree differential coefficients, like example, it should not have things like dy by dx whole square, dy by dx whole cube. Okay, it cannot have d square y by dx square whole power 2 and so on, etc. So these things cannot have. You can have d square y by dx square, okay, but you should not have higher power of that. Okay, because d square y by dx square whole power 1, this tells you it's a first degree second order differential. Okay, and linearity is all about degree of the differential equation but not the order. Okay, so let's see. And third, terms involving product of dependent variable and its differential coefficient Okay, like for example, you cannot have terms like, example, you cannot have things like y into dy by dx. Okay, because obviously this independent variable degree is 1, this is of degree 1, so both are combined to degree 2 actually. Okay, so similarly maybe some y into d square by dx square, you cannot have this y square y cube anyhow, you cannot have, and so on, etc. Okay, so this things should not be there. Okay, so means if you check any term of the differential equation, it should be only of first degree in case of dependent variable actually. Okay, so if in any term, if the degree of the dependent variable crosses 1, then ultimately it's nonlinear. Got it? Examples, we'll write few examples. For the time being, we'll solve only first order equations, but once we move forward, we'll solve higher order equations. Okay, in the maybe in the Wednesday's class. Okay, so let's see examples. So in the examples, maybe we can write it as maybe the first example, d square y by dx square minus 5 times dy by dx plus 6y is equal to x square. So let's say you have this equation. Clear? Something like this. So here you can see this is second order derivative, this is the first order derivative, and this is zeroth order, the variable itself. So in any term, the degree of the differential equation did not exceed 1. Okay, so this is 1, this is 1, and this is 1, and nowhere in this you have the degree to be the degree to be more than 1 actually. So this is called a linear differential equation. Okay, linear ODE. Second, similarly, can someone tell me whether this is linear or non-linear? E power dy by dx is equal to e power dy by dx is equal to, say, maybe some x square. So let's say like this. This is linear or non-linear? E power dy by dx is equal to x square, and you know the expansion for e power x, of course. So come on, quickly tell me, that's non-linear or linear? All of you, everyone, to type it in the chat box. Linear, 100% sure? Yeah, it is of course linear. It's a first order. In fact, you can see this can be written as dy by dx is equal to ln x square. So this implies dy by dx is equal to 2 times ln x. So clearly this is a first order and linear differential equation. Okay, it can be simplified. Third, let's talk something. Say for example, d square y by dx square plus 2x dy by dx plus sin y is equal to, say, e power x, for example. Okay, then in that case, this is linear or non-linear? Please tell me. Is this linear equation or non-linear equation? Come on, quick, bit faster. So come on, do this quick. This is linear or non-linear? It's non-linear, is it? Where is the higher degree term have for the dependent variable? Can you see any higher degree term for the dependent variable actually? It's non-linear or linear? It is non-linear. Okay, so this is non-linear actually. The reason is, when you look at this equation, sometimes it's so nice to get convinced that it is linear, okay, because there is no higher power directly coming up, okay. But if you check this term sin y, okay, this sin y expansion is y minus y cube by 3 factorial plus y power 5 by 5 factorial, okay. So since sin y is actually, the higher powers are in the hidden form, okay, so 3 factorial plus y power 5 by 5 factorial and so on, okay. So this is what, so because that sin y is involved here and that involves non-linear terms, ultimately it's a non-linear equation. Got it? 2x dy by dx is not non-linear. The reason is, you see, this is product of independent variable and differential coefficient, okay. It's not something like this. Clear? In this term, this is independent variable and the degree of dependent variable term is only 1, okay. So the non-linearity is not because of this multiplication of x. In fact, it is linear, but this involvement of sin y gives you non-linearity because of this, okay. Is this clear to all of you? Please type it in the chat box. Did you understand? The non-linearity is not because of this multiplication of x, okay. So this is like independent variable multiplied to differential coefficient, okay. But the non-linearity is because of the presence of sine function actually. So this sine function will actually create non-linearity, okay, because there are hidden terms of higher powers of y inside that sin y. Fine. So let's look at some nice linear equations. So the general form of any first order linear ODE, first order linear ODE is, this is of the form a of x some function in terms of x dy by dx plus some function in terms of x y is equal to some function of x. So let's say c of x. So this is the general form actually here. So linearity depends upon the dependent variable, yeah, of course. Okay, so let's see, this is the first general equation of any form. Okay, so a of x dy by dx plus b of x into y is equal to c of x actually. Okay, then let's see, clearly a of x is non-zero, otherwise if a of x is 0, it's not a differential equation, you have just a equation, a linear algebraic equation, y equal to c of x by b of x. Okay, so that's the case. So this a of x is non-zero, so clearly a of x, clearly this a of x is non-zero actually here. Okay, so a of x is non-zero. So this can be simplified as dy by dx plus b of x by a of x times y is equal to c of x by a of x actually here. Clear? That's what you can write. And in general, this is a ratio of two functions in terms of x. This is also a ratio of two functions in terms of x. So we write this as some function, say p of x or p, let's say p, which is a function of x, of course, and this we'll write it as q for some time. Okay, which is again a function of x. So here this p and q are purely functions of x. So writing this equation in this form is same as, therefore the general form of first order linear equation, the general form of first order linear equation is dy by dx plus p times y is equal to q, where p comma q are functions of x alone. There is no involvement of y in this capital P and capital Q. So these are functions of x alone actually here. So if these are functions of x alone, then ultimately this is the standard form, and this form is given by this name because the person who worked out this is Leibniz. So Leibniz linear equation. So this is called as Leibniz linear equation. Clear? So please give this name. So the Leibniz linear equation is of this form, dy by dx plus p into y is equal to q, where this p and q both are functions of x. Why I'm telling only functions of x? Because if there is an involvement of y here, okay, in any one of this, if there is involvement of y, it can be like multiplication of y into again one more y, so it becomes non-linear. Okay, so that's how we can have the things. Then let's see Leibniz linear equation. So let us see the technique how to solve this equation actually. Okay, so solving Leibniz linear equation. So let's see Leibniz linear equation. Leibniz linear equation, right? So let's solve this. The equation is dy by dx plus py is equal to q actually. Okay, then let's see how we can solve this equation. We can write this equation as dy plus py minus q times dx is equal to 0 actually here. Correct? Can I write this equation in this form? Because if you take this q here, dy by dx plus py minus q is equal to 0. So if you take LCM, dy plus py minus q dx is equal to 0 actually here. Okay, so now clearly if you write 1 here, this function is m of x comma y, and this function n is 1 of course. Okay, so n of x comma y is what you have. So py minus q times dx plus 1 into dy is equal to 0. So clearly this is dy. Okay, so it's not always the first coefficient is m. Things like this can happen. So this is m and this is n, because this is in product with dx and this is in product with dy actually here. Now let's see, consider, because now the next thing is it's a first order equation, m dx plus n dy equal to 0, and clearly it's non-exact. Okay, because why it's called non-exact? Clearly, therefore dou m by dou y, if you differentiate this with respect to y, you have this p, which is some function of x actually here. Okay, and dou n by dou x is equal to 0, because it's a constant. Differentiation of this function with respect to x is 0, and it's not mandatory always that p is equal to 0. Okay, if p is 0, it's fine. Okay, then this case gets happen, but it's not always necessary that this p is always 0. Okay, so therefore in general for some non-zero p, this equation is non-exact equation. Okay, so since p let's say p need not be 0 always, need not be 0 always. This implies if you call this guy to be equation 1, 1 is non-exact, correct? So this first equation is of course non-exact. So can you all convince yourself that this equation need not be exact always? Yes, everyone. So please type it in the chat box. Can each and everyone identify that this equation is need not be a non-exact, is need not be an exact equation always? Yes, come on, type it in the chat box quickly, because this p need not be 0 always, of course. Okay, now if p is non-zero, then what we can do is, let us figure out integrating factor. Okay, so therefore let's try for if integrating factor. Okay, so how we can do integrating factor, let's see. Since I'll use little expertise of mine, consider 1 by n times of dou m by dou y minus dou n by dou x. Okay, so if you consider this, then what is n? N is 1 actually. Okay, so 1 by 1 into dou m by dou y p minus dou n by dou x 0, so which is p, and this p is function of x alone, function of x alone actually. Okay, so clearly you can see this integrating factor whatever we have calculated, this term is equal to p, that's what we got, and this p is purely a function of x. That's what I have exactly told you here. In this case you can see for m dx plus n dy equal to 0, if this term is purely a function of x, then integrating factor is e power integral f of x dx. Okay, so therefore in this case, since it's purely a function of x, therefore if integrating factor of 1. Okay, so this is the Leibniz linear equation. So for the Leibniz linear equation, the integrating factor is actually equal to e power integral p dx. Okay, so p is purely a function of x, so you can do integration of p dx. So this gives you e power some function. Okay, so this is the integrating factor. Now once you figure out integrating factor, what you will do, you will multiply this integrating factor on both sides of the given equation, correct? Let us do that. So therefore this is very important. Okay, so first let us, I'm not sure whether I can mark a line, but if I can mark integrating factor of 1 is equal to, let's write it here, is equal to e power integral p dx is what we have. Okay, so that's the function. Now once you get the integrating factor, and this is important, okay, we figured out what's the integrating factor for this Leibniz linear equation. Okay, so once this is the integrating factor, multiply integrating factor on both sides of given equation to make that exact. Okay, multiply integrating factor on both sides of equation 1. Okay, so once you multiply this, then we get e power integral p dx times 1 into dy plus py minus q times dx is equal to e power integral p dx into 0. This is 0 of course on the right hand side. Okay, now observe something little carefully here. If you expand this, let's see what you will get if you expand this. E power integral p dx into 1 dy plus e power integral p dx into py dx is equal to, this minus is there, so if you put it on the other side, we have q into e power integral p dx to dx. That's what we have, correct? Yes or no? Please type it in the chat box. Can I add this? The only thing I have written is e power integral p dx into 1 dy. Just I have multiplied this e power p dx to all of these three terms, but the third term, since it has a negative sign, I have sent it to the right hand side. That's all. Okay, so once you send this, then we have, you know, this can be written in some form actually here. Okay, so this is actually derivative of y into e power integral p dx actually. Okay, so this is derivative of e power integral p dx is what this complete function is actually. Okay, like if you want, you can check when you are derivative of product of two functions, okay, derivative of product of two functions, actually, let's see, this actually gives you, okay, not here, maybe I'll show a bit separately. Derivative of y into e power integral p dx. So let's say you have this function, okay, then let's start first function into derivative of second function. So first function into derivative of this function, let's write step by step so that you will get it, plus second function into derivative of the first function, okay, so derivative of the first function. So this term is as it is, you can directly sense this, e power integral p dx dy, e power integral p dx dy. So this first term is actually this term. Now if you simplify this, let's see what happens. Y into derivative of exponential function, the exponential function itself, into derivative of the upper function, because this is also some function of x. So derivative of integral p dx gives you a p dx actually, okay, plus this function as usual, p dx times dy, of course, okay. So I'm repeating, when you differentiate this exponential function, derivative of exponential is exponential as usual, derivative of this upper part, because that's also a function, so differentiation of integration gives you the function itself, so which is p dx actually. So which if you simplify, e power integral p dx into this y into p gives you py dx plus e power integral p dx into dy, and this is exactly same as this term, okay. So therefore this complete term can be written as derivative of y into e power integral p dx. Is this clear to all of you? Yes or no? So please type it in the chat box. Come on, a bit faster. All of you, please type it in the chat box. Yeah, okay. So therefore you can write this as, this implies, you can use this maybe as the side result to understand anything that's going on here. So this is equal to q into e power integral p dx dx. So if you observe, q is function of x, p dx will be function of x. So this complete thing will be only function of x actually, okay, because this is purely function of x, this q is also function of x, so product will also be function of x. So if you differentiate, if you integrate on both sides, it tells you integral of derivative is just the function plus constant, because you have removed the integration here. So this is the actual solution. So this is solution of Leibniz linear equation. Fine. So did you get this? It's a simple understanding, of course, okay. So this is how we calculate the solution. So first we'll write, so in general this is something like, per note or else basically summary is something like, per dy by dx plus py is equal to q, solution is y times integrating factor is equal to integral q times integrating factor times dx plus constant actually here, okay. So that's the integral factor, of course. And what about if, where the integrating factor if is equal to e power integral p dx, that's what, okay. So if you put e power integral p dx, because you know p, so you can calculate the single variable integration. So y into if, which is this, is equal to integral q into if, which is this, plus constant, okay. That's all. That's the solution actually for this Leibniz linear equation. So let us solve some questions maybe to quickly figure out what does this Leibniz linear equation tells you. So solve this question quickly. Dy by dx plus y is equal to e power x with y of 0 equal to 1, then the value of y of 1 is dash. Come on, enter the answer. I'll give you maybe 120 seconds. Solve this. If you have understood, it's very easy to solve this. Okay, come on, do. can maybe round off to 3 decimals, let's say. Okay, so let's solve this question. Solution: given dy by dx plus y is equal to e power x, correct? So what I can do, I can put 1 here, that's all. Okay, because if it's y, then it's like 1, of course. Then let's solve this. So this implies, on comparing, therefore on comparing with Leibniz linear form. Okay, so on comparing with Leibniz linear form, p is equal to 1, q is equal to e power x actually. Okay, so p equal to 1 and q equal to e power x. What is integrating factor? Therefore if is equal to e power integral p dx, which is e power x. That's it. Okay, so this is e power x, e power integral 1 dx, so which is e power x. On solving, therefore solution is y into integrating factor integral q into integrating factor dx plus constant. Okay, so this is the constant actually here. Clear? So this is the constant, of course, and if you simplify this, okay, so y times e power x is equal to, this is integral e power 2x, correct? Because e power x into e power x gives you e power 2x. Integration of e power 2x is e power 2x by 2 plus some constant. Now to get this constant, they have given you the boundary condition, given y of 0 is equal to 1. So what does this tell you? At x is equal to 0, y is equal to 1. Okay, so what you're going to do is put x equal to 0 and y equal to 1 simultaneously in this equation. Okay, so if you put x equal to 0 and y equal to 1 simultaneously in this equation, therefore you have, therefore if you put y equal to 1 into x is 0, so e power 0 is equal to e power 0 by 2 plus constant. So c is equal to half is what you get. Okay, so c is equal to 1 by 2. So that's what you are telling, e minus half. Okay, maybe let's see. So c is equal to half is what I'm getting. Okay, if you solve this, because this guy is 1, it is 1 by 2, so 1 minus 1 by 2 is 1 by 2. Okay, so that's what you get. So if this is 1 by 2, therefore what's the value you're interested in? Y of 1. Okay, so y of 1 is equal to y at x is equal to 1 actually. Okay, so let's see, if you put x is equal to 1 in this equation, y into e power 1 e is equal to e square by 2 plus c is actually how much? Okay, c is 1 by 2. So this is what you get actually. So which tells you, if you delete this e, so 1 by 2 times of e plus e inverse, what you get. Okay, so 1 by 2 times of e plus 1 by e, which is e inverse. So therefore y of 1, maybe we can write a small statement here. Therefore y of 1 is equal to half times e plus e inverse. That's all. This is the calculation. So you can get y of 1 value to be some calculation here. So let's do, how much is the calculation? So this implies y of 1 is equal to, let's punch few keys and get the answer, e plus e inverse. E is this plus 1 by e, what you can write, e plus 1 by e. So this is the value divided by 2, 1.543, 1.543. So that's the answer to 3 decimals, 1.543. Okay, because it's basically, it's like cos h1, that's all. Okay, so cos h1, e power 1 plus e power minus 1 divided by 2. Okay, even if you take 1 and type cos h 1.543, okay, that's what you get. Okay, is this clear to all of you? So please type it in the chat box. Is this fine to each and everyone? You all understand? Basically, we have calculated the integrating factor. We figured out the solution, but this is the general solution. Then we have substituted the boundary condition to get the value of the constant c. Once you got constant c, you have put back x is equal to 1. This solution to get y of 1. Okay, so 1.543 is the actual answer. Fine. Okay, so I'll give you one homework question maybe. So this is the question for homework. You can maybe solve it. Okay, you want the value of y at x equal to ln 2. Clear? Round of 2, 3 decimal place. So this is homework question. So please try this question. It's a basically it's a thoughtful question. So in tomorrow's class, what we'll do is, so first of all, in today's class, what we have done is we have looked at exact equations. You have seen the mathematical form for getting these exact equations. Then we have also seen integrating factors to a big extent. Integrating factors. So once you have these integrating factors, then ultimately you can convert. But in fast way, we'll do mistake sometime. Yeah, of course. That's the reason why many of you might not have answered. Check the poll. 1.543. That's the answer, right? 1.543. Yeah, let's check it. I know because many of you might be doing calculation mistake in that way. Okay, that's the integrating factors, and basically integrating factors convert non-exact equations to exact form. Okay, and the last guy you have is exact equations, integrating factors, and what else I have talked today? Leibniz linear equation. Yeah, okay. So we also discussed about the Leibniz linear equation, or generally the general form of the first order linear equations. Okay, so this is of the form dy by dx plus p times y is equal to q, where this p and q are functions of x alone. Okay, and these equations are many times helpful in technical subjects as well. Okay, many times we deal with first order equations. In such cases, this solving Leibniz linear equation is very helpful. Okay, so in tomorrow's class, what we're going to do is, so in tomorrow's class, we'll look at first thing, equations reducible or non-linear equations, basically non-linear ODEs to linear ODEs. We can see how this conversion happens. This is of course some fun stuff for some half an hour, and the main prime focus would be applications of first order equations. Applications of first order ODEs is what you get. Okay, so applications of first order ODEs. These are the two things which we look in prime focus in tomorrow's class. Okay, and with that we finish the first order equations. In Wednesday's class, we'll move on to the second order equation. I mean the higher order. Okay, it can be second, third, whatever. We'll move to the higher order equations. Okay, so is this clear to all of you? So we'll meet again at 7 p.m. tomorrow, and we'll continue this discussion of differential equations. Till then, I'll take a. If you have any doubts, you can ask me. It's open to you now. So, of course, you have been asking all over the lecture, but still, if you want to know something or some portion, you can ask. What is the value of E? 2.718. Okay, and how did you get that? Look. So in general, you have e power x is equal to summation x I equal to 0 to infinity x power I by I factorial. Correct? So if you put x is equal to 1, this tells you e power x equal to summation I equal to 0 to infinity 1 power I by I factorial. So at x equal to 1. So this tells you e power 1 is equal to summation I equal to 0 to infinity 1 by I factorial, that's it. Okay, so which is like 1 plus 1 by 1 factorial plus 1 by 2 factorial and so on, plus and so on till infinity. Okay, so it's the infinite series. So this value turns out to be around 2.718 roughly. Okay, and which if you want the exact value you can get if you click E, 2.71828 up to some 3, 6, 9, 12, 15 decimals is given here. That's how you have. Okay, you have the calculator, virtual calculator, so just click on this guy E, you will get the answer 2.71. Fine. Okay, so is that clear to all of you? Yeah, I hope it's clear and everyone. So then thank you all. We'll meet tomorrow again at 7 p.m. and we'll discuss certain more interesting things about the differential. Okay, so in tomorrow's class we'll talk about applications of differential. They're very quite popular in population development models, okay, or in many cases actually. Fine. So thank you all. We'll meet tomorrow at 7 p.m.